Hello, everyone. Good afternoon. Thanks for joining us. I have the pleasure to introduce our guest speaker, Dr. Scalia. He's an associate professor in civil and environmental engineering at Florida State University, and it's also the CSU Site Director for the Tailings Center. He's here to give us a lecture about the advancing the management of tailings and mine waste. And please have a seat. And without further ado, I would like to invite our guests to start the speech. Thank you very much.
Thank you. So I'm going to talk about tailings. My name is Joe Scalia. As we said, I'm from Colorado State. If there are questions as I'm going along, if I am talking about something that does not make any sense or that you have no context or background on, please raise your hand, interrupt me, feel free to ask points of clarity, etc. I will try to avoid that to the extent possible. If there are questions, we'll certainly have questions at the end. If you have questions before I move on from topic to topic, let me know. If you all look completely lost, I'll probably slow down. If you all fall asleep, I'm just going to assume it's the food. I'm not going to take it personally, and I will speed up to get through the experience faster. Oh, Priscilla. I'm going to make it louder.
Yeah.
All right, fine. Uh-oh. I'm in trouble. Thanks, Priscilla. All right. Yeah. Or I could just talk louder. Okay, can everyone hear me in the back? Heather? Yes. Okay. Am I too loud? Not yet. If I'm too loud, let me know. Okay.
Let you know.
Yeah, I'm just being suddenly too loud. All right, so we'll start off with the safety share. I expected this safety share. Other question? All right, I expected the safety share to be. Oh, it is too loud. Yeah, we'll work it out. A little bit more relevant to the weather. I'm disappointed with our lack of snow, but starting out on the first snowfall, we had our first snowfall this morning in Fort Collins. I probably should have adjusted this to be road construction related, given the state of I-25 as it exists in perpetuity. But winter is upon us. The safety share here is sometimes it's really easy to know it's going to be slippery outside. So this photo is from a couple of years ago from our front yard. It snowed a lot, school got canceled. Instead, I built an igloo and sang Frozen songs with my kids all day. An obvious day that it's going to be slippery outside. Sometimes you don't know, but in the winter, if there is precipitation, there is certainly a chance it will be slippery. So on the right is a video from my driveway last spring semester. It looked pretty. We did not cancel school. Everything was just glazed ice. As a reaction, CSU canceled school the next day when they really didn't need to. And I had two undergrads come into the class with casts on their arms because they had broken wrists in the ice. So if it may have precipitated and the ground looks wet, or even just if it's winter, be careful going outside. Take those first little ginger penguin steps to make sure you know what the conditions are, and then go boldly forth to get to class right on time. But just be careful with those first steps. Happens in Colorado. I went to undergrad in Pennsylvania. This happened all the time. I fell quite a few times on my way to class. Anyway, so moving on to a little bit more of the technical content, I'm going to be talking about tailings, and maybe my biggest take-home message or the hope for the presentation is just to reinforce that tailings shouldn't be an afterthought. And increasingly, they're not an afterthought. In some operations, they've never been an afterthought, but we're going to talk through some of the aspects related to tailings. I'm going to jump around on a few topics so I don't just bore everyone going into the weeds on critical state soil mechanics and static liquefaction of tailings dams. But we're going to discuss why these facilities exist and why sometimes they fall down and how we can avoid that maybe better in the future. So this is an example of a tailings dam. Who knows what a tailings dam is? Good. What's the purpose of these? Anyone? You're all eating. I'm like perfect waiter asking right as you're taking a bite.
Problem downstream.
To kick the problem downstream, but hopefully not too far downstream.
Okay.
Keep the problem where we want it. So the concept of this, right, is after you ground up rock to be finer and finer, to be silt or clay sized or sand sized, and mixed it with a bunch of water and extracted out what was of interest or of value, we end up with a huge fraction of waste. I like the saying that mining is in the industry of making mine waste. And then you also have the side benefit of getting, metals of value. Very efficient processes for crushing down rock and making rock smaller and smaller, mixing that with water, transporting it, and then trying to get it back to a stable landform, trying to get the water out. So these ponds, these storage facilities, they are reservoirs with the sole intention of removing the water and creating a geologic material again. And the best way to do that, the most efficient way to do that, is to pump slurried ground rock into an impoundment and to allow that to consolidate under gravity and just wait. And so these facilities then are designed to just wait. Unlike water reservoirs, they're not built all at once. They're built in stages as the mine evolves, right? That is a challenge because unlike water reservoirs, the materials will change in unexpected ways, perhaps at the original design. And it is a challenge because you don't always know what's going to be underneath there. There's also a challenge, for example, there's also a challenge that they're difficult to modify once they're constructed. And one of the big pressing questions at the moment is, how do you take these apart if you want to, if you realize you need to? In Fort Collins, we sit under Horsetooth Reservoir, a big 100,000 acre foot reservoir right above the city. That would never be permitted today. And I say never, we're probably going to get another big reservoir just upstream of town in the next year or two. So I probably shouldn't say never. But in the early 2000s, when there was an increased awareness of the seismic hazard that existed in northern Colorado, they drained the reservoir, they buttressed the dam, they rebuilt the upstream filtration, and then they filled it back up. Easy peasy. Not easy, a few $100 million, but done. You can't easily do that when the material behind the dam doesn't just drain away magically, or at least doesn't intentionally drain away magically. The reality of what these look like, many of you have probably seen these in person. This is mine in Central America. You see slurry deposited tailings coming off a sand dam that is also constructed out of the tailings. It's just been fractionated to get out the sand to use that as a drainage material and to build the dam. These slimes then are going to settle under gravity. As much of the water as can be is going to be recovered from a decamp pond, and the mine will go on, right? And the problem with these facilities is that if they work, great, we don't worry about them. And if they don't work, we have tremendous problems. And so this figure that I like that I've modified from Carlos Santamarina shows a few of these examples of why we can have problems. We can have overtopping of the dam if water is not correctly managed or balanced, or if the climate does not do what we expect it to do. We can have a geotechnical failure in the dam. What I'm showing here is what's called an upstream raise, which is the most efficient, the lowest cost, the lowest footprint, but also the least stable in many conditions. Or we can have a foundational failure where foundation material either doesn't act as we expected it to, or there's pockets of material that are heterogeneous, that we didn't characterize the engineering properties at that location because things varied in space and we missed it, and where we get behavior that we didn't want. And the result can be videos of failures that get splashed across social media, right? So has everyone seen this video? A few knows, so I'll go through the very beginning. So, right, this is a tailings dam failing under static liquefaction.
Rock on the face. There's a truck and people working on that.
Yep. Yeah. In real time. And a little bit of the better sense of scale. This is a few years ago. Oh, maybe I'll jump to the end. How about this one from a few weeks ago? Right in South Africa. So these failures continue to happen, right? And we're going to talk about that a little bit further. The result of this, as well as increased pressure on the mining industry to be more green, right? And to have different styles, perhaps, of interaction with communities, different engagement with communities, different engagement with the public, has been the global industry standard on tailings management that ICMM member companies have agreed to implement in some framework. The goal of this is to go from the very beginning of mine planning all the way to after the mine is done, after the tailings are covered, after a landform is reestablished. The other goal in here is to have zero harm for people and the environment. So the goal is zero harm. A question exists whether or not we can get there, but a huge focus in the tailing space right now is how do we get there? And part of that is investments, part of that is awareness, part of that is additional technologies. So I'm going to talk today about two aspects of towards zero harm. One is going to be related to design and implementation, and partially related to activities going on at mines, where we need good engineers and we need communication between those that are designing or managing tailings and everyone else involved in the mine. And we need to be doing better at that than we have in the past. The other piece is going to be briefly around technological innovation as an example of some research we've been doing at Colorado State with some industry partners. One example, there are many examples. And again, my goal in trying to cover both is to not totally bore you. So we're going to talk first about design and implementation and talk very briefly about static liquefaction, which is the attributing mechanism to a number of the recent failures. But it's not a new failure mechanism, right? So if we go back, Priscilla was leading a short course and a course earlier this last week, where we went through a case study on a tailings dam failure that occurred in South Africa in 1994. Now, 2 orders of magnitude smaller than San Marco. 2 orders of magnitude is a lot smaller, but these failures continue to happen. So we can't say we didn't know this possibility exists when it's been happening for decades. And it goes even further back. If we go back to Montana, so I'm from Montana. I graduated from high school right around here. If you look at the largest reservoir in the state, the largest lake in the state, the Fort Peck Reservoir, the Fort Peck Reservoir during the dam construction in 1938 failed via static liquefaction during construction and was identified to have failed as static liquefaction, although at that time the concept was new and very controversial. And so there was some good technical fighting in the geotechnical literature about what the cause was. But we've been aware that this exists for going on 80 years. Right? So why does it keep happening if we have awareness that things can fail this way and they will fail this way under certain sets of conditions? All of this comes back to effective stress. So I was teaching undergraduate soil mechanics for a colleague who was out of town earlier this week. I got to introduce effective stress, which is my favorite concept in geotechnical engineering, the seminal contribution of Carl Terzaghi to soil mechanics. My dog is named after the engineer that first published this equation. My cat is named after his lab assistant. My wife would not let us name our son after him, but the dog had already been named. I think I lost that battle. But who's familiar with effective stress? To varying degrees. So the concept here is that soils and tailings or any saturated material, the stress felt by the material is related to 2 components. It's related to the total stress applied and to the pore water pressure. So The total stress is just the composite normal stress on a plane. It's a combination of the soil stress, any loads at the ground surface, and the weight of the water. One way to think about it would be if you took any plane in the subsurface and just took that column of material out perfectly and stuck it on a balance and weighed it, and then divided that by the area, you would have the total stress that was acting on that plane. And it gets a little bit more complex if we're looking at different orientations in the subsurface, et cetera, but a pretty basic stress. The pore water pressure is exactly what it sounds like. It's the water pressure in the pores. And if anyone has dove into a lake before and been amazed that they could pick up a heavier rock from the bottom of the lake than they can above the water surface, you've experienced the concept of effective stress, that you're only lifting the buoyant weight of that rock. You are subtracting the volume of that rock times the unit weight of water. You're not having to pick that up. Or said another way, the effective stress that the soil grains are feeling is equal to this total stress minus the pore water pressure. And this minus the pore water pressure becomes really important, because if we have a lot of water pressure, the water pressure can equal the total stress. And if the water pressure equals the total stress, what is the effective stress? Zero. We can take this in the other direction to unsaturated soil. So in unsaturated soils, Ning Liu, a colleague of y'all's in civil and environmental engineering, has introduced a term called suction stress, which is just the manifestation of capillarity in unsaturated soils. And all that is a negative pore water pressure. So if you have minus a negative, you have a positive. So in an unsaturated soil, the pore water acts to provide a stress to the soil, which is why you can build a sand castle when you have an unsaturated soil, but you can't build a sand castle when the sand is dry or when the sand is saturated. You have this magical range in the middle. The problem for tailings dams is that if you take material that's been ground really, really finely, it has a very low total stress relative to the weight of water, which is to say you have a very small amount of solids per unit volume. You've got a lot of water per unit volume. And so the effective stress provided on planes within that structure is very, very small. If the effective stress is small, then the shear strength is small. If the shear strength is small, you can lead to failure. If you apply enough pore water pressure to liquefy or to equal your total stress, now you have a material that's behaving like a liquid and you have problems. It's certainly more complex, but this is a very fundamental concept in geotechnical engineering. At the end of the semester, I make my students make memes to describe the class. I often get a third of those just related to effective stress and the importance of effective stress in geotechnical engineering. And effective stress is our tailings challenge. But we've known about this and we teach it to undergrads. So why do these fail? Part of the answer is in this upstream construction. If we don't know what exactly was placed here because we didn't communicate it, because we weren't paying attention in the past, because somebody was having a bad Friday and didn't document the deposition or the location of the slimes of the pool next to the dam on that Friday, over the 20-year period that this dam was constructed, and then later on construction happens above it, we can run into problems. So one solution to dealing with this then is we become more conservative and we no longer build on top of those potentially weak materials. We build straight up, or we build downstream even to get things even stronger. The problem here is it requires more material to actually build the dam, and it takes up a larger footprint in locations where often we're space limited. So we've got challenges. Characterizing these old facilities and figuring out where those weak spots are is a challenge. We can do it. It just takes a lot of effort. But to the point earlier on the video, there was a drill rig out at the toe of that dam when it failed. So there's a lot of these facilities and there's a lot of haste needed to get these characterized to make sure that we're not going to run into more problems. There's a lot, yes.
The resilient failure size technical issues. Isn't there ethical issues as well?
Yeah, so in addition to all this, right, there's a whole string of ethical and communication driven issues associated with the actual implementation of construction and whether or not the engineer feels empowered to stop construction, to stop the mine because, say, something isn't happening as it should be during construction. That those communication lines exist across the operation and that they're trusted and that they're followed.
I think there was, and again, I don't want to take to the whole presentation, but I think there was a costly that was supposed to be monitoring and certifying, and they had kind of a kickback scheme that none had happened.
And they had certified recently that the facility was safe.
Right.
Yeah. Yeah, so there's a lot more complexity in here in terms of certification of the facility and the engineering design and certification of stability that happened in this and a number of facilities, well, worldwide.
Question.
Yeah.
The bottom diagram is usually something we get from the textbooks. Is it actually any mind to apply that?
Yeah, there are many mines that do center line construction, and actually there's countries, Chile, for example, where upstream construction isn't allowed due to seismicity, and so we either do center line or downstream.
So it's basically because of the mining law, which one?
Or the law that is governing construction of that facility, but also if built correctly, this is a stable design.
Yeah, like the one in Brazil. Sure.
If not built correctly, it might not be a stable design, right? And there's other complexities in the Brazilian failure. The geochemistry was in play. The material was weakly cementing due to changes in redox condition within the tailings. That wasn't really picked up in the analysis. Yeah, plenty of complexity in here with these type of facilities. Yes.
But it's also predicated on maintenance and water management practices.
Yep.
Both of which were grossly inadequate.
And are likely inadequate at a number of facilities of the at least 17,000 that exist across the globe. There's estimates of these number of facilities up to 34 and even 40,000 tailings facilities worldwide. It's hard to actually get estimates. This is from a student's work a few years ago, and you see there's plenty of countries where we know mining is happening that the estimate is zero because there's not reports on the number of tailings facilities. There's also countries where we have good databases as to the number of facilities that are in operation. The result of this, though, is you've got big complex facilities with sometimes unknown history, and there's a lot of work to be done to assess whether or not all of these are stable given our current set of knowledge and that we're not going to continue to have problems. All while we're trying to ideally mine more with lower grade ores. And so we're going to have more projects coming online simultaneous to assessing existing facilities and what's going on. So part of the Towards Zero Harm is just having good engineers that are out there assessing this. This good engineer would also come into those ethical questions and whether or not we have governance in place that is able to frame those ethical questions and impact some of those ethical decisions, but also that companies are buying into that and realizing that there's a huge risk at play here and that some of those schemes that are either ethically questionable or unethical really are not acceptable and really need to not be at play. So one of the issues in play, and certainly a fun one to talk to at a university, is that we need more tailings engineers. We also need more mining engineers. And so we don't just have one problem here, but especially with these recent failures, especially with increasing size of facilities, and especially with the GISTM and all of the assessment that has to be done as part of that, we have a large need for more skilled folks to work on this. The other problem, and I actually don't know if this exists in the mining industry, it exists in other portions of civil engineering, we have a lot of baby boomers with a ton of knowledge. We have a big drop off after the baby boomer generation. And because of that, we need a lot of people, but it's not just like the university is magically producing competent, fully trained 20-year of experience engineers. It's going to be a long journey to get there. And so there needs to be a lot more teamwork on how do we increase experience quicker? What is the role that universities can play at that? How can we partner with industry? How can we use the knowledge that exists and archive that and disseminate it to the absolute extent that is possible before too many folks retire, before too much of that knowledge is lost? In tailings, a couple of years ago at the beginning of the pandemic, we did a survey to look at tailings engineers, and we ended up getting responses from a little bit over 350 tailings engineering practitioners, curious about what are their years of experience, curious about what portion of the industry the respondents were in, primarily consulting, but also working for mining companies. Curious what degree of education applied to them. So we have a fraction that is bachelor's. The majority of tailings engineers have a master's. That's because, as we'll talk about, a lot of tailings engineers are either civil engineers or geotechnical or geological engineers, primarily civil engineers. And in civil engineering, it's too broad a discipline to give you a lot of deep domain knowledge in soils or in geomaterials. And so there's been a requirement often for a master's as kind of an entry-level degree. I was discussing this with Priscilla a little bit earlier. There's also issues related to, we just don't go as deep today as we might have, say, 40 years ago in a bachelor's in civil engineering. We're covering a whole lot more topics than the technical topics. And so a master's has in some ways become a technical extension, and also an extension, among other things, related to communication and writing and technical analysis and things like that. In terms of those practitioners, the majority were civil engineers, but there were geological engineers. This is an impressive percentage when you consider there's only, 12 geological engineering programs left in the country. Mining engineers, environmental engineers, geoscientists. We have a wide array of practitioners who are having to work together to work on these complex projects. And I would argue increasingly, the huge piece of this needs to be communication among all these, and especially communication with the mining engineers, because a lot of the decisions that the mining engineers, that the metallurgists are making are impacting the tailings, are going to be impacting the tailings, have impacted the tailings. And so those communication lines need to be much more open and more developed than maybe they have been in the past. We asked those practitioners, what is the greatest challenge facing the tailings and mine waste industry? Their opinion was the biggest challenge is labor. And primarily, these were short answers. That labor is having good people, getting good people, retaining good people. Management in general, social license, design safety, mining industry practices, probably all things that if you asked them, anyone in mining, you would get similar responses. So what are we doing about this if we know there's a labor problem? CSU has been working on tailings and mine waste work since decades ago. Started the Uranium Mill Tailings Conference with John Nelson and Steve Apt and others in 1978. That conference is still going on. It'll be hosted in 9 days in Denver. We've got 650 registrants. It's sold out. We've maxed out the venue. So there's activity here. The horrifying thing, we have 650 registrants. Of them, 30 are students. And there's about 10 to 15 academics. So that partially reflects that we've got a conversation that happens among industry. It's also a reflection that we need to be doing a lot more in recruiting and students. We need to be a lot broader. And so that's what's in part led to formation of the Tailings Center, which is a group composed of CSU, y'all, University of Arizona, trying to work together to build more tailings practitioners and to enhance the state of research and knowledge in this area. And this is really, really important. And there are not good multi-university examples of this existing in the world. And especially multi-university examples existing across departments where we've got civil engineers talking to metallurgists, talking to mining engineers. What needs to be happening? And so this is a very exciting development that is continuing to grow and will be really exciting to see where it ends up. And if you have more questions about this, ask Priscilla or Jehan or Linda Figueroa or myself or Chris Bereither at CSU or Cray Luxbacher at University of Arizona. Anyway, part of the activities in this has been education. So we've got educational needs for new students. We've also got training, upskilling that needs to happen within industry. And so there's been a series of short courses offered, multiple iterations to make these better, looking at upskilling related to tailings. And so we'll start next week our closure course 6. A huge piece of these short courses has been asking industry, asking literally hundreds of practitioners to come in and give lectures about their knowledge domains, because they know what they're doing very, very well and are quite happy to disseminate that information, right? In tailings, in particular, the goal is not to have harm, not to have failures. It's not to gain a competitive advantage, to be able to, dispose of my tailings slightly more or less expensively than someone else's tailings. Far better that no one has a failure, because a failure looks bad for everyone. So education is one big piece of what we've been working on. The other part is in technological innovations. Universities function on education and on research. And so research has been a big piece of what we're doing. Another way, aside from doing really good engineering and understanding our systems and carefully monitoring during construction, that we can get away from material that could potentially liquefy, is just to get the water out before we place it in whatever storage facility we're going to end up with. So we've got the tailings continuum, where we increase solids content as we move to the right. Often we end up with what are termed conventional tailings. These are thickened, they've gone through a thickener, but still have very low solids content, very high water content. And we can continue to thicken them to a condition that we would just call thicken, continue to decrease the water content, and we can move to the right on the spectrum. And to the right on the spectrum is filter tailings or filter cake, where we've gotten the material to be unsaturated. We have something that's acting much more like soil in theory, and less like, the muck on the bottom of the pond that you punch through immediately when you step on, right? That's all that we're doing in these classical tailings storage facilities. We're just trying to get the water out. We're, instead of waiting for gravity to do it and waiting decades, centuries, millennia for all the water to get out, we're doing it in the course of a few hours by inputting a lot of energy. So how do we filter tailings? I mean, the concept is very basic. We're going to somehow get the water out of that material. We can do that either using hydraulic means, so we can apply suction and pull the water out of the tailings, or we can do it via physical pressure means, where we're going to squeeze the tailings between some filter screens, and we're going to squeeze the water out of the material. Both of these, depending on how fine your tailings are, can be more or less difficult. You can imagine getting water out of sandy tailings with no clay is pretty easy. If we have a lot of clay, if we have a lot of smectite clay minerals, for example, it is darn near impossible. And there's innovation being had here. There's improvements being had here. These filters are getting larger and larger and larger and larger. Currently, the biggest mine operating using filters is operating at about 35,000 tons per day. There are many, many mines that are substantially larger, an order of magnitude larger. And so this technology needs to advance in terms of the scale. It also needs to advance in terms of other issues related to, what happens when you have a particularly productive day? What happens when you have a particularly wet week and you're not able to just place this as you expected? Lots of design needs to go into this. The other big piece, who's made coffee before with an AeroPress? Right, so the concept here is you grind your coffee, you put it into this little press, you stir it around. There's a filter here at the bottom, a little piece of filter paper or a wire screen. You take a plunger and you squeeze the water through the coffee, separating out the coffee grounds. you have a little bit more pressure and a little bit more aeration. So this gets you a little bit closer to like something analogous to an espresso. If you've done this before, the problem is the smaller the grind, the harder it is to get the water out, the more energy it takes. I had the horrible idea when my daughter was little, she would help me push this every morning, which was really entertaining when she was like 2. And it's less entertaining now that she's almost 6 and she loves the smell of coffee. And every time just ask, can I have that? But I had to be careful of how fine I ground my coffee because she could not press this plunger if I ground it too fine. The same is true with tailings. And so part of the conversation that needs to be had is decisions made related to extraction, related to grinding, very directly impact the amount of energy and the resultant tailings that are going to be formed. And so we need to be having those conversations because there's real dollar values. You can imagine 35,000 tons per day of material that's 75% water. Squeezing that out takes a lot of energy, a lot of cost. But if you can get it, you end up with still what's kind of in the tailing space being thought of as the best available technology, which is you have these stacks, sometimes called dry stacks. They're absolutely not dry. Don't call them that. They're filtered tailing stacks. The water content is pretty close to saturation, at least initially, because the amount of water you take out, the more water you take out, the more expensive it becomes. The thought here is by having a material that is dense from the get-go, you have something that is stable. And so our goal is to achieve geotechnical stability from the very beginning and not rely on a dam. And so diving back just to kind of basic shear strength, we think of our shear strength of our material as being equal to cohesion. Let's assume for a minute that we have cohesionless material, often the case for tailings. So we just have the normal stress times the tangent of the friction angle of that material. We can get a material that is stronger by placing it denser. And a big piece of the reason for that is if we have loose particles, initially, I'll use my knuckle example because I have to use this in every geotechnical lecture. I actually signed that in my contract when I started. If I have loose material and it shears, the particles want to squeeze together before they move. That compresses the water in the pores. I get a positive pore water pressure. Effective stress equals total stress minus pore water pressure. A bigger pore water pressure, the material becomes lower shear strength. If I have lower shear strength, it's more likely to fail. So what I don't want is loose material. What I want is dense material where when I shear it, again, to my knuckle analogy, the particles have to move up and over each other. The water gets pulled, it resists that. I have a negative pore water pressure. Effective stress equals total stress minus negative pore water pressure. The water pressure gets higher. So what I ultimately want is a material that is denser. And if I have filtered tailings that I can place and potentially compact, I can start out with a dense material. So I can start out with a stable material. It is a little bit more complex than that. So we've been having students look at the unsaturated characteristics of these filtered tailings. If a material is more than 80% saturated, so this is a graph of excess pore water pressure during loading versus degree of saturation. As long as my material is less than 80% saturated, I've got enough air that I'm not going to generate positive or negative pore water pressure because the volume will change and that volume change will be accommodated by air. The air will just shoot out of the pores and all is well and good. Once I get to 80% saturation, the air phase becomes discontinuous and all of a sudden I can start generating pore water pressure. So I can't just place this material at 99% saturated and assume I'm going to be good. I need to be a little bit more careful. And we've gone a bit more into the weeds. A few of you, and I don't want to spend too much time to go into the intricacies on this. This is our critical state diagram. So we've got the void ratio, the volume voids over the volume of solids, and the log mean effective stress. The critical state line is the line on which the soil state is critical. This soil will fail. And so if we have a material that is above the critical state line, we know in general that's going to be contractive. It's going to be potentially liquefiable. if we have a material that is below the critical state line, as it moves to failure, it's going to dilate. We're going to get negative pore water pressures, which are going to increase the effective stress, increase the shear strength, and we won't liquefy. So we want all tailings everywhere at all times to be below this line. And what we found is you can exist above this line on filtered tailings if you place the material really, really loose. And so there's not just a magic remedy here that we filter it, we place it, we're done and we're good. There's still design that needs to go into this and care that needs to be placed in the moisture content and the densities during placement. So we need to place it dense. Some of you may be thinking, oh, we have other examples of where we place unsaturated mine waste. We have problems there too. Maybe less so on the strength side, but we have problems with waste rock on the environmental side. And so we also in filtered tailings need to consider that we have a reactive material that could, depending on what the composition is, end up with a condition where we have air, where we have water flowing, and we end up with acid rock drainage. And so we've been looking at that as well. This is a picture of Schmoken Creek in Pennsylvania. This is about 5 miles from where I went to undergrad, so I like the picture. But we're trying to avoid this characteristic orange ARD signature, and especially try to avoid it in a technology that we think of as the best maybe geotechnically, potentially a pitfall that we don't want to go down on the geochemistry. So another research question that we've been looking at is if we can take our waste rock, co-dispose it with our filtered tailings, if the filtered tailings will either stay sufficiently wet or have a low enough permeability to either impede gas flow or impede water movement, can we just solve both problems at the same time? We're adding rock, we have something stronger, we're relying on the unsaturated characteristics or the saturated characteristics of the tailings. And so we've been focused a lot on these tailings dominated mixtures where we've got like raisins floating in oatmeal, the raisins being waste rock, the oatmeal being the filtered tailings. Looking at, does that end up with a superior material? Again, with the concept being the low hydraulic conductivity of the filtered tailings reduces flow, reduces the potential flux of acid drainage. The soil water retention can potentially hold the water content high enough that we have a delicate balance of a discontinuous air phase to impede oxygen ingress, to impede one corner of that acid rock tetrahedron, and that we also gain shear strength by including rock in this material, and so we can end up with something even stronger. We've been looking at this for a number of years at the lab scale, at different lab scales. Some examples of what that looked like. These are from flexible wall permeability tests. You see those rocks just encapsulated within filtered tailings. We've been looking at this at the field scale because the field scale, we know, especially soils, especially tailings, can behave very differently in the field than they do in the lab. This is an experiment that was conducted in Central America. We've got one pile that is waste rock and tailings blended together. We've got one pile that's just waste rock, and we wanted to look at, did this actually prevent acid rock drainage? These ran for 2 years. We went back. We also characterized how the engineering properties had changed. If you've ever wondered how do you characterize the hydraulic conductivity of a soil in a way that we trust we've captured the macroscopic flow features. So if I run an itty bitty test, I may miss that there's a crack right here that's a superhighway for flow. And the best practice for doing that is what's called a sealed double ring infiltrometer, where we run just a really big hydraulic conductivity test in the field. Sealed double ring meaning we have an inner ring. We monitor how much water flows vertically down from this inner ring. We have an outer ring that creates a flow halo, and we quantify the flow versus time. Calculating the gradients gets a wee bit tricky, but we're able to measure the saturated hydraulic conductivity of the material. We did this at the site. Drones are great for getting good field photos. A photo of the drone looking down at the 2 SDRIs in operation. These tests take about 2 weeks of continuous flow. Continuous flow on top of this stack was a little bit extra tricky, but made for a fun project. And then given time jumping ahead, using 2 years of sensor data from those piles, instrumentation of pH, instrumentation of seepage, instrumentation of oxygen and water content, looking at lab data from literally hundreds of saturated and unsaturated tests, looking at unsaturated flow modeling, we're able to try to distill out some practical implications for these. So very briefly, if you put these in a dry climate, they dry out, which is maybe not the most exciting outcome from literally thousands of hours of lab work and analysis. So in an arid climate, your evaporation dominates your precipitation. Even though these go in a little bit wet, you have a big boundary condition that is removing water at the surface. And the outcome is, after some initial drain down of water that was saturated to begin with, so no gas in place, the thing stays dry and you don't get downward percolation of water because your tailings are basically functioning as a water balance. This is the same thing that we do in landfill covers now, or in uranium mill tailings covers or hazardous waste covers. We rely on the natural water balance in arid climates to minimize our percolation, to minimize potential environmental impacts. And so we can get that behavior with filtered tailings, and we can get that with co-disposed filtered tailings and waste rock, which is pretty cool. In a wet climate, the geotechnical stability gets a bit trickier because we need to make sure we're placing things dense enough, because once we keep adding water, it is going to get saturated given the low hydraulic conductivity of that material. But again, if the whole pile stays saturated or near saturated, we don't have oxygen ingress, we don't have runaway acid generation in our tailings. And so we're able to achieve a very favorable condition in wet, a very favorable geochemical condition in wet climates. The geotech here gets a little bit trickier, but Greens Creek in Alaska, which is still kind of viewed as the like gold star mine for its tailings and its filtered tailings operation, is operating in a wet climate with saturated filtered tailings and doing a great job of achieving those objectives. Where things,
just the capping it, I've been talking about filtered tailings for lecturing on it for years, but I always stop when I say, and now this is where it goes to be stacked. And I say, well, they cap it.
Yep.
But if you cap it, does that protect from more moisture? What's the balance on the capping when they, plant soils and trees and that sort of things? Does it balance out the water even in a wet climate?
So what's interesting in the dry climate, actually the hydraulic characteristics we're trying to get out of soils that we would use in a cover to design a water balance cover to minimize infiltration are very similar to tailings. We want loamy soils with generally finer particles, some sand in there. The key just becomes having a growth media that plants are going to be happy with. In the wet climate, that water balance isn't going to do it, right? But we may want the material to stay saturated or near saturated. We can add resistive covers, so covers that are intended to zero the downward percolation of water, if that's relevant for our objectives. That might be something like a geomembrane that's just a sheet of plastic that is resisting flow. It can be a mineral barrier, like a thin layer of sodium bentonite that's sandwiched in there. It can just be soil that's been compacted. But all of those systems, they're integrating with the atmosphere as well. And so in a climate where we get groundwater recharge, where we have an abundance of precipitation and not a lot of evapotranspiration, we're always going to get downward percolation of water through soils. That's what nature wants to do. So we either have to accept that we're creating something that is impermeable, or we rely on that and rely on saturated conditions existing. And then we really get into how do we direct the water so that the whole thing isn't being leached continuously, so that we have preferential flow paths that are directing water out of the system as we intend. And then erosion, I mean, as always on the cover problem. So where this potentially gets much trickier is in these climates where we're between really dry and really wet. So the Front Range of Colorado would probably fall in that arid climate, but maybe Boulder wouldn't. But there are plenty of places in the world, where I grew up in Montana would be one example where we have a climate where we get a little bit of percolation, but it's episodic. It depends on whether or not we had a good water year or a bad water year. And increasingly, as we get to more and more episodic precipitation, we're getting more and more episodic percolation. And that is not what you want. And so that cover feature on these systems is going to be much, much more fundamental to making sure that we don't have percolation, to making sure that we're not having problems with long-term geochemical impacts to the environment. So maybe rounding out filter tailings, the big elephant in the room on filter tailings is still cost, right? The amount of energy required to remove water out of these systems. I remember at Mine Exchange in Salt Lake talking to one of the filtered vendors this past year and them bragging about their filter press applying the force of the space shuttle launching, which is amazing until you think about the energy that's required for that to happen, right? So we need to get the cost down. We need to also figure out how we're calculating costs. If we're using net present value and high discount rates, we're going to end up with things that are unrealistic. We're up to 35,000 tons per day. We don't have a big, large scale demonstration of this technology and then energy and carbon. In the long term, then it's just seeing these get bigger and bigger. Figuring out the fines issue. If you have a lot of fines, they're really hard to filter. So if we grind less, we recover less, but we also have an easier time filtering. And so what does that balance look like? What does that balance look like on a case-by-case basis? And then increasingly a driver on this is water, right? If we're in environments like Arizona, where we have water scarcity, where the federal government is asking us to cut water usage, having a huge evaporation pond sitting there for the next 200 years may not cut it in the future. And so getting the water out now, water is increasingly being viewed and valued in these kind of analyses. And there's lots of questions in here. So the Tailings Center is going to have a meeting next week or 2 weeks with industry related to how do we do better research, road mapping, and tailings. What does this look like? I'm not going to go into these in any depth or even read through the list because you are all capable, but there are many interesting questions in tailings, and it's going to be hopefully an exciting time, hopefully not too exciting though, over the coming years as we try to dive through some of how do we better manage tailings, how do we better educate tailings engineers. So last, and I'm probably over time, a few concluding thoughts. This is a picture from Fort Collins a few years ago. This photo is from noon. This is during the Cameron Peak Fire, where we had this kind of weather for like 2 months straight in Fort Collins. It was awful. But as was articulated at NPR as I was driving down, actually not directly, but we need more mining because we need to decrease our reliance on fossil fuels, if for no other reason, right? NPR did a wonderful job of articulating that we need more clean energy and then stopped right there. We need that mining to be in our backyard, right? Because we cannot be relying on mining everywhere else. We need more tailings practitioners to deal with that more mining and with current mines, and we need them educated to be really darn good engineers so that we don't have failures. I also just want to add this conversation around mining and the need for mining. My perspective coming from the tailings, from the geoenvironmental side, is this is a really fun conversation to have, and especially a fun conversation to have when we include tailings and mine waste in the story, right? That we are quite capable of doing much, much better than we did 100 years ago in terms of how we were managing our mine waste. And that's part of the picture. That's part of what we're thinking about. We need more mining, but we also do not want to trash the environment in the process, and we are capable of doing that. And we need to be given those opportunities. Geotechnical engineers working in tailings, hydrologic engineers, hydrotechnical engineers, environmental engineers, geoscientists, geological engineers, mining engineers, all need to be working together and all need to be developing common vernacular so we're able to have good informed conversations about these issues, which kind of leads back to the tailings can't be an afterthought. We need to be thinking about it through the whole process, and we could spend a lot more time talking about that. Finally, I just want to thank grad students at CSU that have been working on this for the last, since I've been at CSU the last 7 years. We have a great group of students focused in tailings and mine waste. We have an SME student chapter now. So mine students, when you see CSU students at Mine Exchange and they look totally lost, be kind to them. Say hello, have that conversation, develop those networks, and keep things moving forward. Anyway, thanks everyone.
You know, we have some job demographic problem in mining and metals, and that is, the very don't, right?
Yep.
And you're exactly right. We're not going to get out of this quick. And I thought that saying, people are cross-cultivating and cross-communicating and have taking stuff that's all too. Given the legalities and given the potential for assets, could you comment on the role of professional licensing in dam development? That is, when we're building tall structures or building bridges, you have to have someone stamp off on that. It ain't gonna happen. So is the same happening in the tailings world?
The same is happening in the tailings world, and we've got a role called engineer of record, at least in the United States, variable titles elsewhere. Professional licensure is a component of being in that position. But yes, absolutely. The issue I think really is that, professional licensure doesn't show that you have the experience and the credentials necessary to be effective. It's a component of that. But it's not showing that you have the breadth of experience and mentoring and knowledge and team to do this effectively.
Right.
And so, yes, in the professional licensure is important. Accreditation is important. Guiding folks to get that licensure is important. But it's not the end in any way.
No, of course not. The second question.
No, but one thing we're talking about creating a graduate degree in the discussion, is there a profession
Yeah.
that is tailings engineering?
Oh,
Because the size of these tailings and they're far beyond geotechnical. It's far beyond.
Yeah, and there's a P in geotechnical engineering or civil. Is that the right
I
credential?
understand. I'm not, I mean, obviously, a PE license only says you have the minimum capabilities to achieve that, and you need much more. I was just talking about, the lawyers were all over this kind of stuff.
Yep.
Second question, you said you're from Montana, so am I. What are you now? Is that Winifred or Hobson?
Oh, no, I was trying to point at Centerville.
Okay, I'm just sorry.
Yeah.
I thought you were a Hobson person.
Not a Hobson person. A class C person though. For what it's worth. How they're doing coming.
Yeah, depending on where you're working in the world too, the company that's actually designing that or overseeing that also has liability and signs and seals for that and for practice. So it's not just the DOR.
Yep.
It's also responsible. It's the company as a whole has to put a seal on the employee.
And those legalities and the insurance and all of that are becoming increasingly complex. So, right, there's tailings engineers working at insurers, figuring out what those risk profiles look like. There's tailings engineers that are working behind the scenes with law firms. In every capacity that lawyers are in play here. So it's not just the engineers doing design for consulting firms.
So one thing, you have to say something about climate change, Joe, because you can have significant weather shifts and some of these facilities are
Yep.
going to be subject to different conditions in the future.
Yep. I don't think I need to say anything. I think you just said it. Climate change makes it harder.
You have a completely saturated, but it's rainwater still flushing through. That rainwater is going to carry on. So is it still causing mass erosion?
Yeah. So in this type of stack configuration, yes, you're still getting percolation. Ideally, what's happening is to a large extent, you're putting a cover on and minimizing the flux of that. But where we benefit in filtered tailings, the particle size distribution is so fine that the saturated hydraulic conductivities are very, very low. And so the rate at which that we're getting flow through these facilities is tiny. So are you still getting some acid rock drainage proceeding? Yes. How far is it getting into the stack? What does the geochemistry look like? What does the buffering look like? What does the microbial ecology look like within that large stack under those conditions? Great question. And at some point, we probably need to take apart Greens Creek to figure out what's actually happening there in terms of these processes.
Because there's a lot of seepage going on. In
There's a lot of seepage. Yep.
So I have a comment slash question. Like since the water is becoming more valuable and our like the main problem in tailing this water.
Yep.
So why don't also we encourage the research for dry processing, right?
Yeah, absolutely. So if that could get figured out, we have solved a large component of the problem here, right? It doesn't take away all our previous facilities, and it's got to become competitive with existing processes, but certainly there are many more paths here. Why don't we recover a lot of these metals off the earth and bring them back, right? As y'all know far better. Then we're not even dealing with terrestrial tailings.
I have a proposal right now.
The tailors on the moon.
It's not an ignored area.
Yeah, I mean, yeah, for sure, it's not an ignored one, but you know, like what I meant, part of the Tailings Center education is maybe, or the research that we showed some maybe.
So I could get some money from the Tailings Center. I research.
I
And
mean,
get rid of tailings, yeah, solve the problem.
Dry means dust plate, right? So it's not necessarily a.
It's all kind of.
Here's all stuff. The way it is right now, in my opinion, there is not a signature defined practice of what is acceptable. And that's something that grows when you have a practice. Understanding the lawyers. And you look at this, it's a nice,
Knowledge share.
it's like a police one, so.
Yep.
Yeah. Okay, so it's involving.
Should I ask one question? I'm more than willing to stay around and keep answering questions, but I also don't want to keep the audience captive.
One more.
All right, one more. How about two more?
The next, okay, you got good practices, all these, build the plan to figure it out. What's your plan B when it fails? Because nature happens, earthquakes happen, and the Titanic wasn't supposed to stay and it's saying. So what's the plan B? How do we mitigate environmental risk?
Yeah, so I mean, a piece of that, a big piece of that is through instrumentation monitoring. So the whole IoT of monitoring piece that is happening across engineering, across our lives, as my phone is probably listening to me right now, is happening in tailings. So how do we better instrument monitor these systems continuously? But beyond that, the understanding of potential risks, if there are a failure, developing plans for what is going to be done, developing plans for recovery are all activities that are undertaken or increasingly being focused on and are components of the global industry standard for tailing. The issue though, to some extent, is if you have those big catastrophic failures, if there are people that are at risk downstream from those facilities, you have a catastrophic failure. And it's a really hard discussion then to say, oh, we want to have this new mine, but also there could be no one that lives anywhere downstream from this tailings facility. You should let us, mine here and dispose of our waste here. So
I'm from Butte, Montana, and we have a brilliant design for that, because we have a Yankee Doodle tailings dam, and it diverse, goes right into the Berkeley pit, which is contained, so it's.
But the Berkeley pit's volume is only a small fraction of Yankee Doodle, right? It's like 7% of the capacity. So,
Most of the tailings stands that we have, right now, they would not be permitted elsewhere. Alright, and there are only about 3 or 4 major tailings facilities permitted in any year, started in any year.
it's quite, so if anyone is bored later and goes on Google Earth and looks at Butte, Montana, look at the tailings facility that is sitting uphill from the city. And you can also look at the pit, and then if you're ever driving through Butte, Montana, you can go see the pit.
That's where his house is built on those.
I'll see, I struck my view.
Well, one more question.
My question was about additives, your experience for extra credit assignment, but. I know that like having fill mining was based after, I'm sure that does not come without major costs, so is that a way to improve? The like dam parts that is constructed out of tailings themselves, if you have a bunch of finer material?
Yeah, so there's additives become really complex in here, right? Because we're adding flocculants as part of thickening that those flocculants are then going to have a geochemical impact. They're going to consume oxygen, or the microbes that are consuming those flocculants are going to consume oxygen. That can be good. But additives to increase strength, absolutely, if you can get the economics right, which is the huge challenge, and trust that the strength is going to be sufficient, because what you don't want to do is cement the particles weakly and then just set yourself up with an even looser fabric, an even looser dam that when it fails can fail even more catastrophically. So could you build that dam by adding cement, at 5% and have a much stronger structure? Yes. Is it going to work?
I believe it's gonna work for as long as it has to.
For the next 10,000 years, right?
If you think about it, you start off with the initial ones are like what, 10 meters high? You're building dams that are
300?
300, 500 meters high. And the stresses in there are enough to fail that material.
Okay, well, I wasn't thinking that you want to increase the angle of the post beyond what it naturally.
No, just increase the factor of safety, make things safer. Yep.
That was the process.
All right, I'll stop so you're be free to go about the rest of your day. But if anyone has any questions, I'm happy to answer them. Or feel free to send me an email. Feel free to just ask Priscilla questions. Thanks, everyone.
Thank you very much. Yep.